As technologies advance throughout the 20th century, there are a lot of advancements and missions that are going unnoticed. One of those main missions is SWARM. SWARM itself is a four-year, 3-month-long mission that is composed of 3 different satellites, and the primary mission of them is to obtain data for core dynamics, geodynamo process, 3D conductive and lithosphere, and many other things. Although the primary purpose of SWARM is to obtain data to map the most precise map of the magnetic field that we have thus far. This map in turn will give data that is necessary for research in navigation, weather, and also just research of the magnetic sphere itself.
There are many engineering disciplines involved in making these SWARM satellites. Electronic engineering was used to make all the instrumentation along with the solid state of the satellite. Once the boom was extended, there were no moving parts on the satellite. Geodetic or geomatic engineering is the discipline of 3D mapping the Earth. All the data that is collected will be used to make a 3D magnetosphere map of the Earth. A lot of instruments on the SWARM satellites. A few of them are the Vector Field Magnetometer, or VFM, which gave linear and low noise measurements of Earth's magnetic field vector components. Absolute Scalar Magnetometer, which did calibration of the main instrument VFM. Electronic Field Instrument, which is measurement of ion density and drift velocity and electronic field. The accelerometer, which is measurement of non-gravitational accelerations like air drag, winds, Earth albedo, and solar radiation pressure. Laser Range Reflector, which is reflecting quartz prisms as part of the satellite laser ranging network.
The 3 satellites were packed into a breezy KM upper stage and dispensed simultaneously once in orbit. The main rocket was a SS-19, an intercontinental ballistics missile that was decommissioned from the 1970s. Once launched, 2 satellites orbit the Earth at an initial altitude of 460 kilometers and a third satellite at 530 kilometers. The 2 lower satellites scan the magnetosphere and the ionosphere from east to west, while the third provides a second temporal set of data for which the 2 lower sets can be based off of.
SWARM's magnetic data obtained from November 2013 to the end of October 2014 was used to create the 2015 World Magnetic Map. This map was created by the British Geological Survey and the U.S. National Centers for Environmental Data. The map itself was funded by the Defense Geographic Center in the UK and the U.S. National Geospatial Intelligence Agency. It's used by commercial aerospace and military agencies across the world for navigational purposes.
As mentioned previously, the purpose of SWARM is to map the magnetosphere. And the reason for this is because the strength of the Earth's magnetosphere is not constant. In fact, scientists have measured about a 15% weakening in the strength of this shield since about the mid-1800s. Another factor that the SWARM is trying to get into is that the magnetic North Pole is moving its position, and it moves about 60 kilometers each year, and it's moving at an increasing rate. Visible evidence of the interaction between the magnetosphere and the solar wind, which carries ionic particles, is the aurora borealis, the northern lights. When the solar wind and the charged particles enters the atmosphere, it causes a reaction, and we see the light from that. Another impact for geomagnetism is connection with space weather. There's increasing evidence between a correlation of the sun's output and the strength and intensity of climatic events, such as hurricanes, earthquakes, and patterns. The impact on Earth for geomagnetic storms can affect communications, satellites, can take out an energy grid, blow up transformers.
The mission expectancy for SWARM was 4 years and 3 months. However, it can continue on past the time that the satellites run out of fuel. Basically, the mission is complete when they fall out of the sky.